So, hello everyone, and welcome to the second webinar in the Tech Talk series hosted by IEEE Student Chapter at IIT Indore. Today, our speaker is Dr. Samuel McSweeney, an associate lecturer at the International Center for Radio Astronomy Research at Curtin University. Dr. McSweeney received his PhD in 2019 from Curtin University, dedicating to the mystery of radio pulsars. He has authored multiple papers to date on pulsars and other topics of his interest, with a complete list of publications found on his website. We want to thank Dr. McSweeney for taking the time to join us today. And without further ado, I would invite him to begin the webinar. I'll also request participants to keep their questions for the speaker till the end of the session. Over to you, Dr. McSweeney.
Thank you very much. I'll just share my screen again now, and then perhaps if someone can confirm that you can see my screen. Is that visible to everybody?
Yes, we can see.
Yes.
Great. I'll see if I can make it full screen as well. Okay. Well, thank you very much for inviting me to come and talk to you all about my topic of research. Hopefully I'll be telling you something that maybe you've never heard of before, or even if you have heard of it, hopefully you'll hear some new things about it that will pique your interest. For myself, when I started my undergraduate, I may have heard of pulsars, but I didn't know anything about them really. And then I did a summer project and it was about pulsars and trying to detect pulsars with the telescope that we have here in Western Australia called the Murchison Wide Field Array. And I quickly came to realize that pulsars were something where there were a lot of questions about them that hadn't been answered yet. And that really captured my imagination because people had been observing these things, as I'll tell you throughout this talk, for decades, and we have a lot of data on them, but there are some basic questions that we don't yet know the answers to. And that kind of puzzle really intrigues me. I feel like if I can just dig down into the data, I should be able to find out what's going on. So hopefully in this talk, I'll give you a sense of what some of those puzzles are and why I find them so interesting, but also to give you a bit of the history of pulsars, how they were discovered, even how they were predicted in a certain sense, and some of the great science that has come out of pulsars since their discovery. So I've divided up my talk into 3 acts. So just having a bit of fun, as if it were a play. So Act 1 is the history of pulsars, Act 2 is how they're used, and Act 3 is some of the remaining mysteries and open questions about them. So I'll start with Act 1, the history of pulsars. And what I'm going to do is I'll put this timeline at the bottom of the slides in this section. And you can see it goes from about 1930 all the way up to almost today. So this is a story that covers almost a century, and you'll see as we go along that it's a very intricate history with lots of twists and turns. So our starting point is really a little bit before 1930. In the first few decades of the 20th century, physicists had just been discovering the principles of quantum mechanics, this very deep subject, trying to understand how the smallest particles work, how atoms work. And they had made some immense progress in those decades. And so their challenge was to take this new tool that they had developed and see if they could solve some of the big problems of the day. And one of those big problems was working out how stars worked. It was only not even decades before the turn of the 20th century when people were saying things like, we'll never know how stars work. We'll never know what they're made of, things like that. And already before 1930, people had made immense progress. But it was all made possible because of quantum mechanics. So people were busy scurrying around trying to figure out how stars worked. Ordinary stars are one thing, just how they burn, how they give us the light that we see. But there's another kind of star which is very interesting as well. They're called white dwarfs. And most people, I think, have heard of white dwarfs at least. They're very small compared to ordinary stars. So a white dwarf is typically about the same size as the Earth. And they're very dense. And the way we get white dwarfs is when an ordinary star that's below a certain mass runs out of fuel, and then after a few exciting explosions, the core that's left over is very dense. Because there's no nuclear reactions going on in the middle, it's not held up. It's not held up against gravity by those reactions. Instead, it's the quantum mechanical principles that were discovered about how electrons can't occupy the same quantum state. This is now the quantum force that is holding up a white dwarf. And this was worked out in the years around 1930. And on the right, you can see a picture of Chandrasekhar, a phenomenal physicist, who calculated the maximum mass that a white dwarf can have before even that quantum force would not be strong enough to hold it up. And a lot of people didn't like this idea because, as far as anybody understood, once you overcame that barrier, and if it were allowed to shrink even more, then there would be nothing left to stop it shrinking forever, and you would get a black hole. But back then, people didn't really like the idea of black holes all that much. They are a bit upsetting to the physicist's mind, and so they didn't really accept his ideas straight away. And then, only a couple of years later, a new particle was discovered. Neutrons. So we are probably quite familiar with neutrons as being one of the particles that is inside an atomic nucleus, along with protons. And our general picture of atoms is that you've got the protons and neutrons in the atomic nucleus, and the electrons zip around outside. It's quite surprising to me, actually, that even after they had worked out so much about how atoms work, it wasn't until 1932 that they discovered neutrons. And once neutrons were discovered, then the astronomers get all excited and they start imagining up these outlandish ideas where maybe you can have a whole star that's made up just of neutrons. So here is an excerpt from a paper from 1934, which I think is interesting enough to actually just read it out. And you can see this prediction, this new prediction of some exotic object called a neutron star. It says, the new problem of developing a more detailed picture of the happenings in a supernova now confront us. And I'll get back to that supernova word in a minute. With all reserve, we advance the view that a supernova represents the transition of an ordinary star into a neutron star consisting mainly of neutrons. Such a star may possess a very small radius and an extremely high density. As neutrons can be packed much more closely than ordinary nuclei and electrons, the gravitational packing energy in a cold neutron star may become very large, and under certain circumstances may far exceed the ordinary nuclear packing fractions. A neutron star would therefore represent the most stable configuration of matter as such. The consequences of this hypothesis will be developed in another place, where also will be mentioned some observations that tend to support the idea of stellar bodies made up of mainly of neutrons. So I love this phrase, with all reserve. It gives you a sense that they really are advancing a pretty wild view that probably they understood that not many other people would like or would accept easily. But they advanced it anyway, and this is how we make progress in science. We advance a hypothesis, and then we see about going about testing whether or not that hypothesis could be true. And in this case, of course, testing whether or not neutron stars could be real is tantamount to seeing if you can detect one, seeing if you can actually observe one. So here's my little cartoon picture of what a neutron star might look like. You can imagine it because it's so dense. It's like the same density as an atomic nucleus. You could even imagine it as if it were a single atomic nucleus, only one that had maybe 10 to the power of 57 neutrons. Just in case there's anyone in the audience that isn't familiar with mathematical notation, 10 to the 57 means a 1 with 57 zeros after it. So all that I mean by that is that it's an immense number that you probably can't imagine. And the thing about it is that no one had any, even the people who reckoned neutron stars might be real, they didn't have any way of expecting that the neutron stars would be emitting any radiation that we might pick up with a telescope. So that's kind of bad news for coming up with ways to test this hypothesis that neutron stars exist. And finally, in terms of their density, I just want to point out how compact and small these things are. Stars, ordinary stars, we have a kind of sense of how big they are in our imagination when you may have seen pictures of the solar system and you can see our sun as a star, and it's quite big compared to the Earth. And then I pointed out that white dwarfs were about the same size of the Earth. Well, these things are only about 20 to 30 kilometers across. So I can actually get to the beach from my house probably faster than I could cross a neutron star. So they're very, very compact. So then we have a few developments in the succeeding decades, which may not seem at first relevant to this story of neutron stars, but we'll see that it is relevant in a short while. So one of those developments was the development of radio astronomy. During the war period, a lot of effort went into developing radio technology. And in the 30s and in the 40s, radio telescopes essentially were pointed towards the sky for the first time. And we started seeing that there were things in the universe and in our galaxy that emitted in the radio part of the spectrum. So just as a reminder to anybody who is not coming from, who hasn't seen any of this before, what we see when we look up into the sky is all part of this visible part of the spectrum. I hope you can see my cursor. And that's only a small part of the whole spectrum of light. And way down here in the long wavelength part, you get radio waves. So now I'm going to try to flip to this other website here. So bear with me for a minute. Okay, so this is a website you can go to if you want. It's called Gleamoscope. And what you're seeing on the screen at the moment is what the sky looks like to us in the visible part of the spectrum. And then on the right here, there is a toggle, so you can scroll through different wavelengths of light, and you can see how the universe looks. So if I scroll down, maybe I should point out a few features first. Across the middle, that is our galaxy, and all the dark patches are clouds of gas that are blocking the starlight from behind. But this bulge kind of here in the middle, this where it looks like there might be more light behind, that's pointing towards the center of our galaxy. We're seeing the whole thing edge on. And there are stars everywhere, you can see. These point-like things, they're just ordinary stars. So if I go down to longer wavelengths, what happens, first of all, you see is that all those clouds go away, because actually this wavelength can go through the clouds. So our view is no longer obstructed. If I go down even further to longer wavelengths, microwaves, the view changes again. And we start to see some new features popping up that we didn't see before in the visible. When I get all the way down to radio, a large part of that diffuse stuff becomes transparent, and I'm left with this wonderful view of the galactic plane. But also, everywhere else, you can see points of light that look like stars. But in fact, they're not. And so one of the great discoveries, now if I flick back to my slides. So one of the early discoveries when they started using radio telescopes was that there were this plethora of point-like sources, and they had no idea what they were. They could figure out that they were coming from a long way away, halfway across the observable universe. And they actually did figure out eventually that these things were galaxies, or rather the central engines of these galaxies, where these massive black holes lived. And these black holes were eating up material that are falling into it and generating lots of radio emission along these jets. And that's what we're picking up. So they're very, very powerful jets of radio emission. But this took decades to figure out. And in fact, one of the, so we're definitely in the radio waves part of the spectrum there. So one way that they were thinking about studying it is by considering whether they could take advantage of something that you will know familiarly as twinkling. So ordinarily, you've all looked up in the sky, seen some bright stars, and seen that they appear to twinkle. So let me click this. Hopefully this video will work. It's just, this is just someone's recording of a star moving across the sky and twinkling as it goes. So this happens when visible starlight comes through the atmosphere of the Earth, and the atmosphere bends that starlight in a bit here and a bit there, and that's what gives us the twinkling effect. But it was worked out that in the radio part of the spectrum, the atmosphere as such wouldn't do much bending, but there was stuff outside of our Earth called the solar wind, which would cause radio waves to twinkle in much the same way. So they reasoned that, gee, if they could perhaps look at these objects with a telescope where they were able to record it in time, how much it varies in time, they could study not only the object itself, of course, but they could also study this solar wind, all these highly energetic particles that come out of the sun. So that was the idea, and this led to them building a. We're now in 1967, and they built this array of radio antennas specifically for this purpose of studying twinkling of these point-like radio sources, which, by the way, in case I haven't named them yet, they called them quasars. Now, pictured here is also the then PhD student Jocelyn Bell. And she helped build, well, she actually built the first prototype of this array, and then she helped build the large-scale version of it. And it was her job to look at the charts, the actual recordings that they made of the sky with this instrument, to see if she could detect any twinkling of quasars. That was her job. And this is what one of her charts might have looked like. So she had this this squiggly line here. You can imagine a kind of a seismograph setup where you've got just some kind of pen on a page and responding to the electromagnetic signal that's coming from the antenna and just wiggling up and down. So she would go through by hand reams and reams of paper with these squiggles on it. And she would have to figure out what was what could have been a quasar, what could have been just some car turning on down the road that would have made some interference. And you can see she's marked some interference here. And as she was doing it, she noticed that there were some squiggles that didn't look the same as the interference. Well, it did look a little bit the same, but it had a peculiarity to it. And this was that it kept appearing in the same part of the sky. So on these charts, these numbers here represent actually sky positions. The array is kind of sensitive to whatever sky is passing overhead. And so she noticed that always in the same part of the sky, at this coordinate, there was this scruff, she called it. And she kept seeing it again and again. And so she thought, no, this is not interference. This is something real. And so she would tell her supervisors about it. And the supervisors would say, no, it's just interference. Don't know what you're talking about. And she would say, no, look, it's real. It's real. And there was a bit of took some time to convince them that it wasn't just interference. And so she thought, right, okay, what I need to do is speed up the recording. So the setup was you had this paper feeding through the machine and the pen making this recording on it. But if you fed the paper through faster, then you get a higher time resolution of the recording. So she thought, right, I'll try that. And when she sped up the recording, she found the following. Those squiggles that she found, which she thought was not interference, was actually made up of pulsars. Now, this is probably a little bit upside down to the way we would view them these days, but you can see, hopefully, that along the line that is closer to the top, there are these pulsars that dip down, and they look like they're very regular. So she measured how far they were between each other, and she found that they happened about 1.3 seconds apart from each other. So she made this note on her page: first observation of pulsars from this source on this date. And she probably didn't realize at first just how important this discovery was. So she convinced the supervisors that it was something real. They had discovered a new type of source that apparently switched on and off every 1.3 seconds or so. The question is, what were they? She had called them pulsars just because of the pulses that were on her chart. So now the next thing is to figure out what could be causing them. And as we do mostly for fun in astronomy, that every time we see a signal where we don't know what it is, we can say, oh, one hypothesis is that it's aliens. Of course. In fact, they had a nickname for their signals, LGM, which stood for Little Green Men. And the main reason why they even jokingly considered this was because the pulses turned out to be very, very regular. They always kept to this 1.3 second cycle. And so that sheer regularity made them think, maybe it's artificially created. So that was one hypothesis. A second one is that maybe you could have a star that was literally pulsating. So that is a thing. We know that there are stars out there that literally pulsate. However, all the stars that we know of that pulsate on timescales much longer than 1.3 seconds. But still, that's a hypothesis worth considering. Another one is that maybe you've got something in a binary orbit system, and somehow maybe the 1.3 seconds relates to the time it takes for one revolution to happen in such a system. The only way you could really make that work is if the system is really small, but yet again, it's just another possibility. And the final one you consider is that maybe it's just a single object, but rotating once every 1.3 seconds. So we have these four possibilities. There may be others, but these are perhaps the first four that they were considering. So when you find a new object and you don't know what it is, the first thing you do is see if you can find any more of them. And it didn't take them long to find more of them in the sky, in different sections of the sky. Now, importantly, they had different time between the pulses. So the first one they found had 1.3 seconds. The second one had some other amount of time between the pulses. We call that time period a period. So we'll say that the first one had a period of 1.3 seconds. The second one had a period of whatever it was. It might have been half a second or something else. The third one they found had something else again. And so they pretty quickly thought, right, this is obviously a real thing, but there's no reason to think that any of them are connected to each other. So it's probably not aliens. We can rule that one out pretty quickly. Also, the second possibility with the pulsating star. So as far as they understood at the time, the physics of how the stars pulsate, there was just no way that they could come up with a scenario where you would have that pulsation happening that quickly. So they tentatively ruled out that possibility as well. Now, in both of the remaining cases, you still have a very similar problem. You need these systems to be very small in order to make them work, very compact. And so both of these types of systems were on the table. Perhaps the favored one was the bottom one, where it's just a single object turning around, because it's easier to get a single object that compact than to have a binary system being that compact as well. But how would you really make sure you can prove that it's one and not the other? This is one way that turned out to be the way that they found. And that's to consider what happens to these two types of systems if it loses energy. It must lose energy because we're seeing light that comes from it. Light is a kind of energy. So if the top one is losing energy, what happens? You have to perhaps to get an intuition, you might prefer to think of, for example, what happens to a satellite around the Earth if it loses energy. Does it go further away from the Earth or does it come towards the Earth? And as you probably can imagine, if it loses energy, it will eventually crash onto the Earth. So in orbital systems, losing energy means the whole system gets smaller. But when it gets smaller, the actual time it takes for an object to go around becomes shorter. So this kind of binary system predicts that if you were to observe it for long enough, you should see the time between the periods get shorter and shorter and shorter. But exactly the opposite is true for a single object rotating. So in this case, if it loses energy, it's losing rotational energy, then the rotation will slow down, and you would expect that the time between the pulses gets longer and longer and longer. So which turned out to be true? It turned out that the period did in fact get longer and longer and longer, although they had to observe for quite a while before they could make that measurement, because the rate at which it would slow down is very, very slow. In fact, the time when one of the first examples of these weird pulsar objects that they could really show solidly did this was one that they detected in the middle of the Crab Nebula. And so suddenly we had this example where it seemed to tick all of the boxes for this other crazy idea that someone had, that maybe pulsars, maybe these objects that were small and spinning, maybe they were neutron stars. So in the example of this Crab Nebula pulsar, it was in the right place. So supernovas are places where you expect they are the result of the explosions that happen when a massive star comes to the end of its life. And if you remember back to the prediction, it was that neutron stars are the end result of a transition from an ordinary star to a neutron star that happens during a supernova. So they found one right in the middle of a supernova remnant, this Crab Nebula. It also had the property that the period got longer and longer and longer. And this was the real clincher, is that they could figure out how much energy was being lost from the rotation just by measuring the rate at which that period slowed down. And prior to this discovery, there had been other calculations looking at the nebula itself and realizing that some of the things that were happening in it required a lot of energy. And some people had done some calculations and they had worked out just how much energy would be needed to explain the observations of the nebula. And they had real trouble coming up. The number they had calculated was very, very large, and they had a lot of trouble coming up with any scenario that could provide that energy to the nebula. And then comes along this pulsar observation, and the amount of energy that the pulsar was losing turned out to match the amount of energy that they had calculated the supernova remnant, the nebula, was gaining. So this was a bit of a slam dunk in terms of the neutron star theory. So at this point, everyone was happy. We had discovered what neutron stars, what pulsars were. They were rapidly rotating neutron stars, and and then the question is, okay, so let's try to understand these objects more. Let's see what we can do with them. Let's see what they can teach us about other kinds of astrophysics. So this next section is about maybe one or two ways that pulsars have been used to study a different facet of the universe. So just to remind you, though, the key point here is that the rotation of the pulsars is extremely stable. You have a very, very massive object spinning quite rapidly, and that represents a lot of angular momentum. It's very hard to change that angular momentum. we've seen that the system is losing energy, so it is losing angular momentum as well, gradually, very, very gradually. In fact, this plot I've put up to show you just how gradually it is. So on the x-axis here, it's the period, it's the time between successive pulses. And all of the purple dots here are actually showing all of the pulsars that we have discovered to date. So back then there would only been about 3 or 4 dots, but now we've discovered a lot more, obviously, so there's a lot more here in this plot. But on the y-axis is how quickly it's slowing down. So, and I've made the units here, very importantly, to give you a sense, seconds per million years. So I hope you can see my cursor. Where it says 10 to the 0, that means 1. So any dot that's along that horizontal line there means that a pulsar will lose 1 second of rotation every million years. So that's an extremely slow slowdown rate. And really, realistically, within any of our lifetimes, because of that slow slowdown rate, none of these points is going to move very far around this diagram. That you would have to wait 1 million years to see it move appreciably through this diagram. So these are very, very stable. And then this pulsar here that I've circled in red, this is a special pulsar that was discovered in 1975. So again, just re-emphasize that mostly what you expect to see is that you see this gradual slowdown of the pulses. This one is no exception. On average, it does that as well. However, they noticed that as well as having an average slowdown, it also did something like this. Sometimes it would slow down, sometimes it would speed up, sometimes it would slow down, sometimes it would speed up. And so that got their, they were scratching their heads over this one for a little while. They saw that it happened regularly. So they measured how long it took for one of these slowdown periods to get to the next slow period. And it would happen about once every 7 hours and 45 minutes. So they're like, okay, this is now confusing. We have something that is spinning, and you can see if you put your draw a vertical line from that point on the plot, you can see that it's about 0.05 seconds. So that's how fast it's spinning. It takes 0.05 seconds to make one rotation. However, something else is happening on a 7-hour, 45-minute time scale. And so they figured out that one way you could get that is if the object itself was in an orbit with something else. So perhaps you've got the neutron star orbit, maybe, for example, in the red, and maybe it's in orbit with something else that we can't see in the blue. And then what would happen is every time the pulsar is on a part of the orbit where it's moving towards you, then that would serve to speed up the apparent pulses, because every time the next pulse happens, the pulsar is a little bit closer to you. So it takes less time for that light to get to you. And then the opposite would happen when it's on the far side, moving away from you. So they calculated from those periods just how fast the pulsar would have to be moving away from you or towards you during one of these rotations, one of these 7-hour, 45-minute periods. They put it on a plot like this on the left. Radial velocity is just what I said. It's just how much it's moving towards or away from you. And the black line is a fit for a particular shaped orbit. So they got an almost perfect fit. They were able to work out the shape of that pulsar's orbit just from measuring the time of arrival of those pulses, which is phenomenal. And it was only possible because of just how reliable the pulses would come in, and how well you can measure the times that they arrive. Then very quickly, so after they published that in 1975, very quickly everyone realized that this orbit, which I'll show again, is really small. And if it's in a binary system with another object, the whole system is very small. These are very massive, dense objects. It might be that this system would be giving off something that Einstein predicted called gravitational waves. So as they move around each other, for example, the system is expected, according to Einstein's theory of general relativity, to give off gravitational waves, which is making, it's actually extracting energy from that system. Now, they realized that we wouldn't be able to necessarily detect the gravitational waves directly because those waves would be very, very, very faint. And we don't have any means, we didn't have any means back then of making that detection. However, there would be some other observational consequences for this possibility that gravitational waves are really emanating from this system. One of them is that the system itself would shrink. So you have something in orbit, you extract energy, and the orbits get smaller. But the other possibility also is that the extraction of energy is going to have a measurable effect on the rate at which the orbit itself moves around. So generally we have elliptical orbits in systems. They're not always perfectly circular. And the point of closest approach and equivalently the point of furthest, the point at which the object is furthest away, that point can change over time. So they realized that since they could measure the orbit itself so accurately, just by measuring the times of arrivals of the pulsars, maybe they would be able to detect the kind of any change in the orbit, like it's shrinking or its motion around, like in the right diagram. So that's what they set out to do. Now, obviously, you're going to need to look at lots of data to do that. Like you can't just observe a thing for 6 months and expect to make that measurement. If this thing is happening, it might be happening on years, a timescale of years. So you have to be observing for that long. That's what they did. So they made these observations, and this plot is showing actually their measurement of the rate at which that the point of closest approach is moving around the system. So they have data spanning from 1974 all the way up until 1981. And the line is the prediction of general relativity of just how much that should happen. And you can see that it's a very, very good fit. So this was work that actually won the Nobel Prize. I forget exactly which year it won it, but it's a phenomenal result. So general relativity, you should realize though, there are lots of theories of gravity out there. General relativity, even by that point, was far and above in terms of the number of things that it could, that it predicted, way more accurate than all the others. But there were other theories out there as well to try and explain some of the things that general relativity had difficulty with. And after this paper, it was like, yeah, okay, general relativity is a clear winner here. Now, that was kind of an indirect detection of gravitational waves. They just kind of inferred that the gravitational waves must be emanating from the system by these other measurements. So perhaps most of you will have heard that 5 years ago, we actually made the first direct detection of gravitational waves. And that was made with this instrument called LIGO, the Laser Interferometer Gravitational Wave Observatory. And this system detected gravitational waves just at the final end, between the final few seconds of before two either black holes or black holes and neutron stars finally crashed in the middle, because all of their orbital energy was taken away from gravitational waves. And it's just that final bit where the waves get really large in amplitude that they were able to detect it with this instrument. And there's a picture of their detection plot. So yes, we have now discovered, we have now made direct detections of gravitational waves. Happily, that was in 2015, which was almost 100 years exactly after Einstein predicted that gravitational waves were real. But the thing that perhaps most people don't realize is that gravitational waves, like light, come in a spectrum. So you can have different wavelengths of gravitational waves, just like you can have different wavelengths of light. And the kind of wavelength that LIGO detected is right up here on the right hand end of that spectrum, as it's plotted here. And you can see they've mentioned pulsars and compact binary systems as the sources of these gravitational waves that they detected. But you may also notice, if you let your eye wander around the plot, that pulsars make another appearance. And it says that it's got here down that pulsars apparently might be used as detectors of gravitational waves as well. And the kinds of gravitational waves that pulsars might detect could be caused by binary supermassive black holes in the early part of the universe. So I want to explain very quickly how we might do that. So here is a picture on the left of some gravitational some galaxies that are merging, and we can just imagine that this is happening in the early part of the universe. Those supermassive black holes in the centers of those galaxies will eventually come together and collide and generate gravitational waves. This would make some very long wavelength waves passing through our space, our local space. And the idea is that if we keep track of a bunch of pulsars that we can time really well, then perhaps we could measure whether or not there's any gravitational wave passing through our space. So this is the idea, and it's been an idea for the last few decades. And I'm sorry to say that this experiment has not yet finished. So hopefully I can't even make a prediction of how long it will take, because you need years and years of pulsar data to really be confident that what you're seeing is not some other weird behavior of the pulsar, but really a gravitational wave. So with any luck, some of these experiments that are happening right now will also be able to claim to have detected gravitational waves, but of a different wavelength than the LIGO detections. There's lots of groups around the world doing it. There's a group called NanoGrav, the North American Nanohertz Observatory. There's a group in Europe, the European Pulsar Timing Array. There's one here in Australia called the Parkes Pulsar Timing Array. And these three got together recently to make the International Pulsar Timing Array, because they finally decided it would be better to share their data rather than just racing to the answer independently. And very recently, in fact, India joined the group. So I think it's the first Asian country to have joined the International Pulsar Timing Array. And they're using the GMRT as their main instrument for that. So this is all very exciting research that's going on at the moment. And with that, I'll leave now the story of what pulsars are used for, and move to what are some of the mysteries of pulsars that are still out there. So all that stuff I just talked about with gravitational waves, whether you're measuring the gravitational waves of the pulsar systems, or whether you're using pulsars as gravitational wave detectors, either way, in a sense, if that's what research you're doing, you don't really care how come the pulsars are there in the first place. All you care about is that they're very, very steady, very predictable. This is a kind of a weird situation to be in. It's kind of like the universe has handed us this amazing tool to study some awesome physics and awesome astrophysics. And you can do all of that astrophysics without actually caring about the physics that is happening right near the pulsar itself, that actually makes the beam of energy that we see and that we measure. But this is I don't know, I think this is a fundamental question that we still need to answer. Just how do we get such bright emission from these pulsars? So this is the question that I'm concerned with in my research as well. It's trying to understand those physical processes that would give rise to the radio emission that we see. And really, at the end of the day, there's only two things you need to invent an emission mechanism, a way of generating light. All you need is a charged particle or many charged particles, and you need some way to accelerate them, to give them energy, let them accelerate in some way, and that acceleration will produce photons that will produce light. And happily, we have good reasons to think, good theoretical reasons even, to think that actually around a neutron star, around a pulsar, there is an enormous number of charged particles. I'm not going to go into those reasons today because that would take a whole other hour. But there are charged particles in the vicinity of the neutron star. And also the magnetic field of the neutron star, we believe, with very good reason, to be very, very strong. And magnetic fields are excellent at accelerating charged particles, usually by making their trajectories curve. And a curved trajectory is a kind of acceleration. So the picture that I've got on the right-hand side is actually a picture of a kind of radiation mechanism called synchrotron radiation. It's well understood, it's well accepted. A lot of the radio light that we see from our galaxy comes from this process, synchrotron radiation. And it seems on the face of it that pulsars or neutron stars, there's no problem. What's the problem? We've got magnetic fields, we've got charged particles, we can make radio waves. Great. But of course, it doesn't turn out to be that easy. The problem is actually just how bright pulsars are. And the line of reasoning goes something like this. So the brighter light that you need to come out of it, out of a system like this, requires that the particles themselves have extremely high energies. But what happens in systems like this, like in the synchrotron radiation picture, is that the more energetic the particle is, in this diagram, it's an electron, then the more likely it is to be a catalyst for a process which turns low energy photons into high energy photons. And that process actually robs the electron of energy. So it's a kind of a cooling process. You have something that's highly energetic to begin with, but the higher energy it is, the more likely it is to undergo an interaction which will lower its energy. So it's a kind of a self-regulating process. And this process has been worked out to really give a practical upper limit on how bright or how energetic this population of electrons could be. And if it's too bright, then all of the energy will get dissipated very quickly and you won't be able to maintain that bright radiation anymore. So this theoretical calculation has been done. We have observations of just how bright pulsars would be. So the question is it enough? And the answer is no. Pulsars turn out to be 10 to the power of 13 times, at least 10 to the power of 13 times brighter than this theoretical regulation limit. So this is a problem. There is a possible solution. And it goes a little bit like this. So what I've just described is kind of putting a limit on just how much energy you can get out of one single electron or particle. But if the particles are just doing their own thing and they're zipping around the magnetic field in their own way, there's no real reason to think that the light that's coming out of each of them is going to be coordinated in any way. And when you have a bunch of electromagnetic waves and the peaks and troughs of that wave are just kind of randomly coming out randomly, when you add them all together to make a single ray of light that you can observe, the peaks sometimes cancel with the troughs and you end up with something that's only a little bit bright. But if you can somehow manage to make sure that the peaks and the troughs line up correctly, or in just this nice way, for example, like it is in lasers, then when you add them together, you can get something way more bright. So this seems to be the only way we can get something as bright as what pulsars are. We call the first type an incoherent process and the second type a coherent process. But these are really just words to describe a process that we still don't really understand. And the challenge is, and the unanswered challenge is, to figure out how to make sure that all of the particles, all of the charged particles in the environment of the pulsar are somehow coordinating their emission so that all the peaks and troughs line up. And this is a big problem, an unsolved problem. And every time the observers make a suggestion, then the theorists come back and say, no, that doesn't work. So no one has reached consensus of just how this coherent process happens. So this is the picture so far. We have a spinning neutron star. We have a bunch of highly charged, highly energetic charged particles, which is what I mean here by relativistic plasma. And they're all moving around this magnetic field and flowing along the magnetic field lines. And on the other hand, we've got this beamed coherent radio emission. And the challenge is to figure out how we get the beamed coherent radio emission from that relativistic plasma. And one of the challenges for doing any kind of investigation into this problem is that the energies required are so high that it's just impossible to do any kind of experiment in a lab on Earth. It's just frankly impossible. The energies are just too high. We can't generate that much energy in a lab. So this is the only place where we can study relativistic plasmas of this energy. And it's an ongoing problem. So this has been known since pulsars were discovered. There was this question of, okay, well, how do we just get that much energy and turn it into radio emission? There is a clue. There are lots of clues, actually, and this is one of the frustrations of working with pulsars, is that you have lots of data and not many answers. So the picture I've painted so far is that you have this single beam coming at you, and every time the pulsar swings past your line of sight, you see a pulse of energy. So that's one picture. But it turns out in reality that when you observe pulsars, that beam, or rather that emission pattern, looks far more complicated. So this is just a simulation still, but it doesn't look like there's a single beam of energy coming around like a lighthouse, but maybe that there's some complicated structure in that beam. And the upshot of that complicated structure is that what we observe often, not always, but often, in many pulsars, is this weird pattern of diagonal stripes once we stack all the pulses on top of each other and look at it like a picture. Here is some actual real data, not just a simulation, so you can see what I'm talking about. This is the same pulsar observed at the same time using the MWA, which is that telescope here in Western Australia, and the GMRT, which of course is in India. We observe them at two different frequencies at the same time, and you can see that band structure coming through nice and clearly. You also have this weird thing where sometimes it decides to turn off and on. In fact, pulsars are very individual. They have personalities, and they do what they want, and it's up to us to try and make sense of them. So this is the game that I play in my research. Is I look at these patterns, these drifting patterns, and I try to infer from them something about where the emission and when the emission is taking place. So the idea here is, if we can figure out from those patterns where in this environment of the pulsar the emission is happening, then that would tell us also something about when the conditions for coherent emission must be being met, if that makes sense. So it still perhaps isn't, even if we found out exactly where they were, where all the emission was happening, whether it was high up here or low down here or along certain magnetic field lines or along other ones, that wouldn't immediately suggest any particular coherent emission, but it would be a big clue to finding out which of various theories is the correct one. So in our particular case, there's one particular model called the carousel model. And it suggests that perhaps only a certain subset of magnetic field lines are the ones that are ever active at any one time. And so this little animation is meant to be showing, imagine some magnetic field lines twisting around, and at some point they will intersect the pulsar's surface. And so these little sparks that you see that are rotating around the magnetic axis in magenta is meant to represent the points on the surface or near the surface where some electrical activity might be happening that would generate sufficient number of particles that could produce the emission that we see. So there's a lot of steps in that chain of reasoning, but the game that we play is to look at these drifting patterns, like what you see on the right, and try to match it up with the number of these sparks that are happening in this circle. So, for example, perhaps around this region, maybe there's, I don't know, 12 sparks in a region, and then maybe up here that suddenly drops to 11. Maybe that's what's going on. Or maybe there's the same number of sparks always, and the rotation speed of this weird carousel is changing. So these are the games that I like to play. And fingers crossed that eventually it will lead to some real understanding of the emission mechanism. So in summary, when it comes to pulsars, I guess the takeaway message from all of this is that at the end of the day, they have been extremely useful tools, but they have left us, as all good things do, they left us with more questions than answers. And I think that will always be true, always in any aspect of science, which is a good thing. In our particular case with pulsars, there appears to be more data than theory. So there's a whole decades and decades of observations of pulsars. They're all unique. They're all slightly different. And at the moment, we still don't have a single theory that can manage to capture the huge variety of pulsar behaviors that we see. So it's very exciting in that sense, is that there's always going to be some object that might provide that vital clue to help us figure out some of these long-standing problems. Pulsars are, as I said, one of the only places in the universe that you can study such high-energy astrophysics. And there are others. You may have heard of black holes, for instance. The environment of a black hole is also very highly energetic, but I think pulsars are more fun. So with that, I'll leave it with you, and thank you very much for listening, and I'll take any questions that people have.
Thanks a lot, Dr. McSweeney. For this. We have a couple of questions from the participants.
Yep.
I'll unmute them one by one, and then maybe you can answer their questions.
Okay.
Yeah. Vedan, I'm going to unmute you, and you can ask your question.
Meanwhile, the rest of the participants, you can raise your hand and we can find you out easily.
Do we have the binary systems with the compact object, both the compact object being pulsars?
Yes, we do. So as it turns out, that one example that I showed, that first one that they discovered, both of them are neutron stars, but one of them, for whatever reason, either it doesn't have a beam of emission, or perhaps it does, but it just doesn't happen to be going past us. So that was an example with two neutron stars for sure. They were able to work that out because in order to get the orbit right, they had to work out the masses of both of the objects. And the masses of both of them were consistent with the masses of neutron stars. Okay. However, they're very rare, these systems. I think we do have a system where we can see the beams from both pulsars. We do have an example of such a system, but they are quite rare. Most of the time, sorry, yes?
So ATFN pulsar catalog might have these cataloged?
Yep, absolutely, yep.
And my other question is, when they get their spin, when initial system is formed, so the spin of the pulsar is only to do with the initial spin, right? It's not. Is it affected like with any other mechanism apart from losing energy through pulsar rotation?
Yep, it's a little bit of both, but mostly the first. So actually, all stars have spin, but even our sun has a spin. I think it rotates once every. I'm going to get it wrong. It might be 11 hours or something. But the really interesting thing is that it's the when an object is made compact, that angular momentum has to be conserved. And it's exactly the same as if you've seen ice skating and they're spinning around and their arms are out, and then they pull their arms together and they spin faster. Exactly the same thing. So during the supernova process, a lot of that material, much of it gets expelled, but also much of it comes down and forms that central compact object. But all of the angular momentum is conserved. So even if the original star had a very modest rotation, after that compaction, you end up with something that's spinning of these speeds. But there are also pulsars that spin even faster than the ones I've been talking about here, and they can have rotation periods of only milliseconds.
Millisecond pulse.
Yeah, exactly. So those ones, they have worked out that most of those ones are in binary systems, and that they have taken angular momentum from the companion at some point during the evolution of the system. So that happens when, for example, maybe you've got two stars, one of them turns into a pulsar. It doesn't have a particularly fast period at that point, but then the other one, once it goes through its evolution and becomes perhaps a red giant, that material can get siphoned off and pulled onto the other, the pulsar, and make it even faster. So in this way, we get a population of millisecond pulsars. So those periods are thought to come from stealing the angular momentum from their companion, but the ordinary pulsars with periods of about a second, that would just come from their original angular momentum.
Okay. And can you comment on the Pelletron system? So you might heard of, there are some observation where there's a binary system. There's a one neutron star or pulsar, and other is either a white dwarf or a red giant, and it's feeding it's feeding on its star system. It's a star, right?
Yeah, it's did you say the name of it?
Pelletrons. So this paper was from, I think, a few people from University of Delaware.
So I'm not sure I'm knowing exactly which system you mean, but from what you said, it sounds like exactly the kind of thing I was just describing, where the pulsar is taking the material off the companion. Or was it different in some way?
Yeah, so it was different in some way. So I mean, I have read this paper long back, so I don't remember.
Okay.
So okay, fine. Thanks for.
Yep, sure.
Thank you, Vedant. You can mute yourself. Now I'm gonna unmute Gurpreet, and you can ask your question.
Hello.
Hi.
Yeah, so my question will be very naive. I'm not in this field. So the question is, we know that the magnetic fields are very strong in neutron stars, and these are made up of neutral particles. So the question is, how something which is made up of neutral particles can sustain a magnetic field?
That's a good question. I have two possible answers for you. So one of them is that although I said that it's only made up of neutrons, that's not quite true. So like any chemical reaction or physical reaction, there's always going to be a small number of so when the neutrons were made in the first place, they actually were made by protons and electrons coming together. But there's always going to be a small proportion of the neutrons which are separate into electron and positron, electron and proton. So there will be a small amount of, I say small, but a small fraction of 10 to the power of 57 neutrons is still quite a large number of of electron proton pairs that are free to move around this what's supposed to be a highly conductive material and generate those currents to make the magnetic field. So that's one possibility. The other possibility I read, and to be honest, I'm not sure which of these possibilities is the more true, because I don't study the neutron star interiors. But the other possibility is that the neutrons themselves are producing this this magnetic field, and the way they do that is because even a single neutron does have a magnetic moment. So because even though the electron and proton, or if you like, the quarks that make up that neutron are coupled, it's still possible for that system to have a positive or a non-zero magnetic moment. So the sum of all of those magnetic moments from all of those neutrons together could add up to something very powerful. And that's essentially the same idea as how a bar magnet would work. Like, you don't actually have any large-scale currents happening. You don't have loose charges that are able to move around the material. But even in a bar magnet made of iron, all of the tiny currents are just the atomic currents, and each atom has its own magnetic moment, and they all add up, sum up to the large-scale magnetic field. But again, which of those two scenarios is actually what's going on, I can't really comment on.
Yeah, so I have another question that can you just tell me what is the temperature structure of a neutron star? I mean, is it uniform throughout the core, or it's some kind of
Oh, it is complicated. In fact, this is yet another branch of research. So I believe, and I'm really just quoting high-level stuff that I've read, that at the very outer layers you have a thin iron crust, and then as you get deeper and deeper, the pressures get higher and higher, and that iron crust goes to a superconductive neutron soup. And it's possible that in the very deepest layers, you have something even more exotic, where you've got a quark soup. So where the pressure is so much that even the quarks are not tightly bound into neutrons. This is the broad picture that I've seen, but beyond that, I couldn't give you any more detail.
Okay, so I just one last question. Basically, if there is a matter distribution, you are saying that, and the core of the neutron star, we have a quark like quark soup, something like that. So, is it possible that there will be some kind of temperature gradients which could create some kind of convective instability inside the neutron star?
I believe so, yeah. Also at play inside the neutron star is meant to be these what they call frozen magnetic field lines, so that the whole ensemble is I'm afraid I can't explain it very well because I don't understand it very well. But yes, there's going to be a temperature gradient. There's going to be pressure gradient, and apparently all of the parts of the interior, they're somehow pinned or frozen to this magnetic field. And the reason why they think that is that sometimes there's the equivalent of a neutron star quake, I guess, the neutron star version of an earthquake, and some of that pinned material becomes unpinned momentarily, and it produces such a change in the configuration of the internal structure that it does momentarily slow down the whole pulsar. And we can actually see this. We call it a glitch, and we see the period between the pulses very regular, and then suddenly they get longer, and then they gradually go back to being what they were. So we think that that is evidence of the interiors of the neutron star undergoing this massive reconfiguration.
Yeah. Okay. Thanks for a nice talk.
Thank you.
Thank you for that, Gurpreet. Next question is by Adarsh. I'm gonna unmute you now, Adarsh. You can ask your question.
He's still muted, I think, Parul.
Okay. Well, let me try again.
Am I audible now?
Yes.
Yes.
Yeah. So I am not pretty much, accustomed to this interface, Cisco WebEx. I am using it for the first time, so yeah, some technicalities might happen. So please bear with me as I ask the question. Yeah. So hello, sir. I wanted to ask that, like, where do we stand in the understanding of the internal layers, or you can say the internal composition of pulsars or millisecond pulsars? Just like, you just told us that didn't go into very much detail about that thing, but still, you can tell us.
Well, I just thought maybe I could do some quick Googling on your behalf.
Yeah, sure, sir.
Because so if I pull my screen across here, I've just Googled neutron star interior. This is probably going to give you more detail than I can give you just in words. But I think this question mark here is very telling. It's there's a lot of unknowns here.
Yes.
So yeah, really the only way to study the interiors are via these glitches, what I just described earlier. And it's actually almost the same as the way we can study the Earth's interior by studying earthquakes, because those waves are propagating through the Earth. But here the problem is a lot more complicated, because we don't have a good understanding for how such dense material reacts under certain pressures. So one of the big open questions, which I didn't mention at all in this talk, is a problem called the neutron star equation of state. And what that means is precisely that we would like to know what the relationship is between pressure and temperature. What if you set the pressure, if you set the temperature, how does that material behave? So this is almost completely unknown. There's lots of theories about how it should behave. In fact, if I can show you a plot, neutron star equation of state. And each of these lines that you see on the plot like this represents one model of how the neutron star material would behave. And interestingly, on the y-axis, they have the mass of the neutron star. So each of these models predict that there's a different maximum mass that a neutron star can have, just in the same way that Chandrasekhar predicted the maximum mass that a white dwarf would have. And so what they try to do is the only way, one of the best ways we have of figuring out which of these models could be true is by finding pulsars with greater and greater masses. And if we find one, for example, up here at 2.5, then that would mean that all of these models down here, which end before you get to 2.5, couldn't be true. And that's really one of the only tools we have for finding out more about the neutron star equation of state. But there's, again, big question marks in this field of research as well.
Yeah, I got it. Yeah, and I wanted to ask one more thing. You just told a previous contestant regarding this, that about the magnetic field. It has really intrigued me for quite some time now. I just wanted to ask you this, that I have, there are certain sources which are, available, just like you showed me a certain source right now, Google. So I Googled this thing. I have frequently Googled this thing about how this, magnetic field gets generated in a particular neutron star, or you can say, magnetar. So there, I have found some explanations which state the fact that, certain particular alignment of the neutrons inside of the neutron star. So can you comment on that? Like any specific arrangement or something? What does it pertain to?
I'm afraid I can't really comment on it. I don't know enough about it. My guess is that it's the same argument as again what's applied to an ordinary magnet, in that even in an ordinary magnet, you somehow need the individual neutron, the individual magnetic moments of the atoms to line up in the same way in large regions across the whole magnet. So it sounds like that's what they're arguing as well for the magnetars, is that if it's the neutrons contributing their magnetic moments to the overall magnetic field, that that they would have to have come up with some way to ensure that the those magnetic moments, which are like little vectors, have to line up the same way. But I haven't read that paper, so I'm afraid I can't comment any more on that one.
Okay, thanks a lot.
Thank you, Adarsh, for your question. Sam, I have two more questions for you before we call an end to the webinar.
Yep.
Number one is, if there is an amateur astronomer who wants to access pulsar data, is there some way where, or some source from which they can download such observational data?
Yeah, there is. So a lot of the time, the way it works with, at least in radio astronomy, is that once an observation is made, usually at the request of a professional astronomer, there's a proprietary period where that data is embargoed, and then after that period, it becomes public domain. So as long as each individual facility has a way of providing, like a web service of providing that data, then anyone can download it. I'm pretty sure Parkes has a good one. I haven't looked to see what telescopes do and don't have their data available. I know that the Parkes radio telescope does. The MWA doesn't have an easy way of accessing it, but it's really a question of, if you know someone that works with MWA data like me, then you can just ask for any data that's beyond that 2-year period in our case, and happy to give it. And I think the other one I'm aware of, there's a similar telescope in America, which is also a low frequency radio telescope, and that's called the Long Wavelength Array. And I've seen their website as well, and they have a really nice interface for downloading their data. So yeah, it's just a matter of Googling and finding out what's there, or else finding your nearest astronomer and asking. And more often than not, any non-proprietary data, everyone is happy to share.
Thanks. And one last question. So people generally differentiate between science and engineering when it comes to astronomy. Now, how would you think engineering helped understand science in this particular case?
Immensely. So there's an astronomer who I've met a few times. He was around during the whole time. Like he's obviously quite elderly now, but he was around at the time when pulsars were being discovered. And he pointed out that every time a new discovery in astronomy is made, it's made because someone has made an instrument of a new kind to find something else. So the process sounds like this: someone has made some kind of discovery, whatever it is. They want to investigate it further, but they know that they're going to have to build a new type of telescope in order to study it. So then they get together with the engineers, design, build a new kind of telescope, then start using it, and then find something else that they weren't expecting. And this has happened like the whole way through the history of astronomy. And it's happening even now. I can't tell you any details because we've only just put in a paper about it. But with the MWA, we found something that looks kind of like a magnetar, except that the time between the pulses is 18 minutes. And that's just unheard of. No one's ever seen anything with a period that long. But it only was discovered because of the peculiar way that a survey was being conducted, not even to find pulsars. It was completely different. But they found this object, and now they're redesigning the survey in order to find more of them. So it's this constant feed-on process. And at every stage, new instrumentation has to be built in order to exploit the features of the new kinds of objects that we want to study. And that definitely requires a strong collaboration between engineering and scientists. In Perth, where I am, in my institution, we actually have the engineers and the astronomers working side by side. So the MWA telescope is run out of our department. And every other day, I'm talking to one of the engineers about one aspect or another about the MWA so that I can do my science better. So yeah, absolutely strong connection.
And that's fantastic. Now I think our discussion has led to one more question from the participants, and I'm gonna unmute Vedan again to let him ask his question.
Yep.
Hi. So I have this question. So are these mergers specifically you can say short gamma ray burst or other mergers are more likely to give away, or we can understand physics better than when I say physics, I'm considering question of states or nuclear physics, nuclear pasta we people call, than what we study in pulsar in magnetars.
Yeah, yeah, the answer is definitely yes. So I think even so, after they first discovered or made the first detection with the gravitational waves, for instance, and I think with a couple of black holes, and then it didn't take long before they made some more detections where it was clear that it was two neutron stars colliding. And they realized it was two neutron stars colliding because they also were able to detect it with light. So they had some some ordinary telescopes, some non-gravitational wave telescopes also pointing at the thing, and they made some measurements. And they were able to infer immediately some of the processes that happen inside of the the supernova. The supernova that would have happened there. And they found that a lot of the heavy elements that we already understood came from supernova explosions, but there was a lot of open questions about that process. And so they were able to study directly because of the merger that they detected with the gravitational wave. They were able to study more directly just how much of different kinds of elements were produced, of heavy elements, gold, etc.
Yeah.
But all of that is only possible because it does give insight into the structure of the neutron stars originally before the collision. So I think it does feed into it, though I think it's a very big challenge to try and extract that information about the equation of state from those studies.
Okay, but is it we were able to put more constraint on the equation of a state by studying this 170817?
I think there was, though I can't remember for sure. I think there was some discussion of it. Yeah.
Okay.
I can look up the paper and see if I can find it.
So I have one more question. So what are the current understanding of fast radio burst?
Haha, that is a good question. I don't know if everybody listening knows what a fast radio burst is. Just to be very brief, in case someone hasn't heard, they're extremely bright single bursts of radio waves. They look like pulsars, except they seem to come from much further away, halfway across the galaxy again. And there's an open question about what they are, whether they're neutron stars or whether they're something else entirely. There's a lot of ideas. This is a case where there's more theories than data. But at the moment, things seem to be converging on the idea that they probably are neutron stars. There are many fast radio bursts that repeat. And I think very recently there is some evidence that there might be some regularity to that repetition within a single burst. They've seen some spiky emission where it happens regularly, and so this is encouraging for the idea that they are neutron stars, but it's not a slam dunk by any means. But yeah, that's a big open question.
Is there could be a correlation between gamma ray repeaters, soft gamma ray repeaters, and FRBs?
There's a bunch of people at my department that are looking into those possibilities. So far as I remember, what they've looked at with the MWA, there does seem to be a possible connection, but it hasn't been proven yet.
Okay.
Yeah.
Thank you. Thank you for.
Okay. Yeah, thank you, Vedant, for your questions. It seems like we had a really good discussion so far. Stretched out for almost half an hour. Thank you, Sam, again for this webinar, and we learned a lot, and I hope everyone enjoyed this as well.
Well, thanks for having me. It's been lovely.
Okay. Yes, so it has been really great. Now I am going to end the webinar, and I think we can end the recording as well. Okay, great. All right. Okay. Adarsh has said thanks a lot. All right. Okay. Thanks a lot again, Sammy, and everyone else for joining this webinar. It has been really wonderful. Okay.
Okay. Thank you all.
Bye.
See you later.
See you later.
Thank you, Sam.